Yeah, good morning. So in the last class, we have discussed about the lead compensator. So today we discuss about the lag compensator. Okay. So these are the, as we told that electrical networking devices, which is lead compensator and lag compensator. So here, if you consider this electrical network for this kind of lag compensator, I have resistor, then one more resistor, then I have capacitor, so this is the input voltage which is given as ei of t, and so there is a current flow I of t. Then output is measured between two elements. This is E naught of t. Okay. So if you write the equations, that is voltage equation, input voltage, so EI of t, if you look at EI of t, so current passing through this resistor 1, and this is the resistor 2, and this is the capacitor. So the voltage across the resistor 1 is going to be I into R. I into R. So I of t into R1 plus I of t into R2 plus 1 by C integral of I of t dt. So if I apply the Laplace transformation, for the above equation. So what will happen? Laplace transformation of ei of t is equal to R1 is a constant, Laplace transformation of I of t, and R2 is a constant, so Laplace transformation of I of t. Then 1 by C is a constant, so Laplace transformation of integral of I of t dt. So then this is written as ei of s, which is equal to R1 into I of s plus R2 into I of s plus 1 by C into I of s by s. So if I take out the I of s common here, I'll be getting R1 plus R2 plus 1 by s into C, or C into s. So this is the input voltage equation. Similarly, if you write the output equation, that output is measured, that is E naught of t is measured across the two elements, that is R2 and C. So I into R2, I of t into R2 plus 1 by C integral of I of t dt. So here once again, if you apply the Laplace transformation, for the above equation, apply Laplace transformation for the above equation, I'll be getting Laplace transformation of E of t. R2 is a constant, so Laplace transformation of I of t plus 1 by C Laplace transformation of I of t dt. So this I am going to get E naught of s is equal to R2 into I of s plus 1 by C into I of s by s. So if I take out the I of s common, I'll be getting R2 plus 1 by s C. So this is the EI of equation. This is the E naught of S equation. So transfer function for the given network. So transfer function for the given network. Transfer function to the given network is E naught of S by EI of S. So we need to write the what is E naught of S? E naught of S is equal to I of S into R2 plus 1 by SC divided by E of S is equal to I of S into R1 plus R2 plus 1 by SC. So these two will be cancelled out. So I'll be getting E naught of S divided by EI of S is equal to which we can take C R2 plus 1 by SC. So I can take out this if I take the LCM, so I'll be getting 1 plus R2 into RT into C into S, RT into C into S divided by R1 plus R2 into SC plus 1, because the SC and numerator SC and denominator SC will be cancelled out. So I'll be getting 1 plus S into R to C divided by 1 plus S into R1 plus R2 into C. So if I take out this R to C common outside, so I'll be getting S plus 1 by R2 into C divided by, here if I take out the R1 plus R2 take out commons into C, so I will be getting R1 plus R2 into C. So here S plus 1 by R1 plus R2 into C. So this is the which I am going to get. So E naught of S divided by EI of S, which can be written as R2 by CC will be cancelled out here. C will be cancelled out. So I'll be getting R2 by R1 plus R2 into S plus 1 by R2 into C divided by S plus, here I'll write R1 plus R2 by R2 into R2 into C into R2 into C. So this is 1 by, once again this is 1 by R2 into C. So if I write beta is equal to R2 by R1 plus R2, and then we'll take the T is equal to R2C. So if I substitute this beta and T in the equation, in the above equation, I'll be writing, so this 1 by beta, because if I take this R2 to the denominator, so 1 by beta into S plus 1 by T divided by S plus 1 by this R2 plus this is going to be beta, this is going to be beta, so R1 plus R2 by R2 is going to be beta, R1 plus R2 by R2 is called as beta. Okay, so based on that, if you substitute 1 by beta, and this will become 1 by T, 1 by C. So here this always is greater than 1, and here if you plot this in the pole zero plot, as we discussed in the previous lead compensating network, we have the numerator roots are called as zeros and denominator roots are called as poles. So here at S is equal to minus 1 by T, it is a 0, and S is equal to minus 1 by beta T is a 4. So in the previous lead compensator is also having the same kind of, so at say this is going to be pole which is minus 1 by beta T, and here it is 0 which is minus 1 by T. See here also it is lying on the left hand side. So the designed compensator is same. Now, similar to that previous, what we have found out is maximum lead angle. So here also we are finding the maximum lag angle and at what frequency we are going to get. So here, if I write the equation, that is E naught of S, E naught of S divided by E I of S, which is equal to 1 by beta S plus 1 by T divided by S plus 1 by beta into T. We have got like this. So if I replace this 1 by beta and take the LCM, so I'll be getting 1 plus TS if I take the LCM, and here the beta will be cancelled out if I take the LCM, and I'll be getting 1 plus beta into TS divided by beta, right? So this beta and this beta will be cancelled out. I'll be getting 1 plus T into S divided by 1 plus beta into T into S. Now what I'm doing is replace S by j omega, replace S by j omega. So E naught of j omega divided by EI of j omega, which is equal to 1 plus j t omega divided by 1 plus beta into t, of course, j omega. So if I take the magnitude of this, so magnitude of given transfer function, that is E naught of j omega divided by EI of j omega, which is mod of 1 plus j t omega divided by mod of 1 plus j beta t omega. So here we are going to get root of 1 plus omega square t square or t square omega square divided by root of 1 plus beta square and t square omega square. For the same phase angle, as we told that the phase angle, numerator angles are added and denominators angles also are added if you have more than one, and subtract the denominator angle from the numerator angle. So that is a rectangular coordinates as a phase angle, which can be written as d pi is equal to tan inverse of omega t by 1. So I'll be getting omega t only. Then minus of this, minus of this. So tan inverse of omega into b into t or bt omega, beta and t omega. Okay. So here this we are finding the maximum lag angle. This is lag angle. This lag angle is we are going to find out at what frequency, the maximum frequency, that is pi m, maximum phase angle at maximum frequency. So we are going to find out the d pi by d with respect to omega at omega is equal to omega m. So equal to 0, then I'll be getting the maximum phase angle pi m. So this is according to the maximum theory, according to the maximum theory. So by applying the tan inverse x, 1 by 1 plus x square, so we will be getting similar to that in the previous class. So by solving all those, we are going to get omega m is equal to, in this case, 1 by t into root of beta. So or otherwise we can write as square root of t into square root of beta into t. Okay, so this can be written as square root of 1 by t into beta t, which is so it is nothing but omega m is equal to, we can write as omega c1 and omega c2. Okay, square root of omega c1 and omega c2. So these are the corner frequencies. Omega c1 is equal to at 1 by t and omega c2 is equal to 1 by beta t. So that's what we got, the s plus 1 by t divided by s plus 1 by t omega. So beta beta t. So this is how we can find out the corner frequencies at the maximum phase angle. So here this is about the lag network and lead network. So these two are there in your syllabus in the module 3 itself. So now we'll move on to the state variable concepts. State variable concept. So in the till now we discussed the what you call frequency domain approach, and as well as time domain approach, time domain methods. All we have studied to study the behavior of linear time invariant systems. That is for LTI systems. So we have studied the LTI system, that is linear time invariant systems. So here, in order to study the behavior of this linear time invariant system, we have used the time domain methods, and as well as we have used the frequency domain methods. We have used the frequency domain methods. So these two are called as conventional methods. You can say it is conventional methods. But it has its own limitations in the conventional method, because we are ignoring the initial conditions. We are ignoring the initial conditions. See, these approaches we have so many limitations. One is ignoring the initial conditions. We are ignore the initial conditions while solving these problems, because, say, for example, Laplace transformation of d by dt, f of t is equal to, we have taken s into f of s, neglecting the initial condition. So in all the time domain approach as well as the frequency domain approaches, we have taken the initial conditions are ignored. Initial conditions are ignored, but these initial conditions are very much required. And also we have done for single input and single output. We have done for single input and single output. And for the multiple input and multiple MIMO systems, we have not done this conventional approach. See, the inputs maybe multiple inputs you will be having, or output may be multiple outputs. So in that case, this conventional methods which I have discussed, time and as well as frequency domain methods, will not be applicable. And also, as we mentioned here, this is only applicable for linear time invariant. Linear time invariant means where the time is constant. So there's no the system behavior does not change with respect to the time. So assuming that, and also the behavior is linear behavior. So these are the some which we have discussed till now. Which we have discussed till now, and also we have discussed the root locus, Bode plot, which will not give the Bode plot, and these are all not give the optimum solution. It will not give the optimum solution, which is a trial and error method. So these are the limitations by the conventional methods which we have discussed till now. So what in order to overcome these methods, these limitations, one more method which is called as modern method, we can say it is a modern method which we can apply, is we can call it as state space representation. State space or state variable analysis or state space analysis, whatever you can say, state space analysis or state variable analysis. So the modern method which is going to use to overcome the limitations which are said above, by using the conventional method approach, that is time domain and frequency domain methods. So here in the state space analysis, generally the advantages of this state space approach is where we are considering the effect of initial conditions. So at time t is equal to 0, so what is the effect of this initial condition on the system? That is also will be taken into the consideration. And also this state space can be applied for non-linear system and also time varying systems also. So nonlinear systems as well as time varying systems. So we can apply this state space method, and also it can be applied for multiple input, that is MIMO systems. It can be applied for MIMO systems, multiple input and multiple output. So for any type of input which you have considered, we can design this kind of state space approach. So we can consider any type of input. So whereas in the time domain approach, we have discussed the four standard inputs, but in this case, we can consider any type of input for the design of the system, So any type of input can be considered for the design of the system, right? So now, this also, of course, this method is basically, it involves rather than differential equations, which is in the time domain and the time domain methods. Here we can use the linear algebra or matrix algebra. We can say matrix algebra will be used here, so that we can do using the by MATLAB also. You can easily adapted by the any softwares which are computers can, you can do the computations. And also the vector matrix notation is going to the representation is vector matrix representation. Here the state variables are represented in the vector matrix form. So this is easy to represent in a mathematical representation of the system. So the vector matrix which are going to use in this state space analysis or state variable analysis. So these are the advantages by using this state variable analysis. So whereas in the conventional methods, which we have had the limitations, so to overcome these limitations, we are going to use the modern method, which is having the advantages of considering the initial conditions into the design of control system, and also this can be applicable for nonlinear systems, and also it can be applicable for time varying systems as well, and it can be applicable for multiple input and multiple output systems, and any type of can be considered for the design of control systems. So whereas in the time domain we have discussed the step input, ramp input, parabolic input, and impulse input. These are the standard inputs which you have discussed in the time domain methods. So in this case, we can use any type of input for the design of control system. And also basically it involves the matrix algebra. This method involves the matrix algebra, so it will be easy for computations. And here the notation means the variable notations is in the form of vector matrix, which is the easiest way of mathematical representation of any system rather than representing the differential equations. So it can be represented in the form of vector matrix. So now we'll come to the what is a state variable analysis. So before going to the state variable analysis, the word what is meant by state? So the state, so suppose if you have the what you call at which particular point of time, means at a, as the system is having t is equal to 0 at this particular point of time, and as the time increases, so the behavior of the system, at this particular point of time, how it behaves, what is the behavior of the system at this particular point of time. So that is what we can say state of the system. So if you look at the system in which output is not only dependent on the input which you have given. So here the output behavior also it is depends on the initial conditions at time 0. So the behavior depends on the time t is equal to 0. So these systems are called as dynamic systems or systems with memory or dynamic systems. So in suppose when we say the systems, dynamic systems, you can say dynamic systems. So system which is having, I mean the output is does not depends on the initial conditions. Those systems are called as static systems. The systems are called as static systems, means it doesn't have any dependency. The output behavior is does not depends on the initial conditions, whereas the output condition is depends on the initial conditions, which are called as systems with memory or dynamic systems. Now we can say for what do you say, in this case the mechanical systems, if you consider, so this is the mass m is moving by applying the force F with velocity v, and of course the displacement is x. So here is the friction force or a damping force which you are taking is zero friction here. You are taking as zero friction here. So if you take this equation, F is equal to, we know that acceleration m into a, and m into d by dt of v of t we can write, or otherwise we can write v of t is equal to integral of 1 by m integral of f of t dt. F of t dt. So here velocity at any time is the result of the force applied on the body, force applied on the particle or object or a body. So here v of t, if I equate this, I mean if I use this integration concept for the time minus infinity to t f of t dt, this can be split into two things, that is minus infinity to at time 0. So here this is the minus infinity and t is equal to 0, and here it is t is greater than 0, t is greater than 0, and I am finding the at particular time t, what is the state of the system, what is the state of the system. Okay, so here if I split this into two integral parts, that is minus infinity to 0 f of t dt, then 1 by m, I have taken out n by m, okay, so plus 0, mean t naught or t naught to t f of t dt. Okay, so here where we can take this t naught as initial, this t naught is taken as initial condition, initial time or initial conditions. So we can take this as, this one is going to be taken as v of t naught, v of t naught. So 1 by m integral of minus infinity t to naught f of t dt is taken as v of t naught. So the above equation once again can be written as v of t is equal to v of t naught plus integral of t naught to t f of t dt. So this is how we can of course find out the 1 by m. So this is, see here, velocity equation is written in this form. So we can say it is very clear that the input f of t, which is the input f of t is the output is depends on the depends on the initial conditions as well, and as well as input. So initial conditions are, we can say, memory effects, which is going to be influence the behavior of the system, So the state can be regarded as, it is a concise representation of the past history of the system. So here if you take the state of the system at any time t, we can say combined effect of values of all different, say minus infinity to t, and as well as minus infinity to t. So we have a combined cumulative effect of all these values from minus infinity to t, which we can take it as state of the system, which is associated with the initial condition, because minus infinity to t, integration of minus infinity to t, in the sense where the value starts from minus infinity and then till t. So in between we have 0 also, means This we can say it is a initial conditions, and time starts from 0 to t. Time starts from 0 to t. So mean t greater than 0, t greater than 0 up to t equal to 0, we can be considering as memory effects. We can say considered as memory effects or initial conditions. So thus the complete state of the system we can consider to be a vector having x of t. Say for example, say if we have defined as a vector x of t called as a state vector. This is say state vector. The variable x with variation from minus infinity to t. So all the values we can take it as means the complete state of the system which you have taken in the form of having the components x1 of t, and these are the variables which influence this state vector, x2 of t, and so on. There are xn of t. So what we had considered is having which are the variables of these are the variables of the system, which are considering this as the variables of the system. If I take any system which has the variables say x1 and x2 and so on xn, then the state vector of that system is taken as x of t, which is represented in the form of vector form, that is x1 of t, x2 of t, and so on xn of t. So that is how we can represent the state is nothing but at any time t. At any time t, the state or behavior of the system is called as state vector. So here these x1 of 2 or x1 of t and x2 of t and so on xn of t are called as, we can say, variables of the system or state variables of the system, given system, and x of t is called as state vector. Right. Now, if the state is t2, it has changed from t to t1 means now at t1 I want to find out the state of the system. So for this we need to have at t is equal to 0 what is the state of system, and then we can have the t is equal to t1. So t0 to t1 means t0 to t1. What is the increment? We need to have the knowledge of the input at t1. If I want to find out, I need to have t0 to t1 what is the behavior of the system. So this new state which is x of t1 will become act as an initial state to find out the state at any time t is greater than t1. Means if I want to have greater than t1 means say t2 and t3 and so on. So this x of t1 will become the initial state for these systems. At time t2, at time t3 and so on, where I am finding the state of the system. So at t is equal to t1 will become initial state for that system. Similarly, if I want to find out at t is equal to t2, then t2 will become the initial state of the system. Then t3 and t4, where we are going to find out for these values, this t2 will become the initial state of the system. So this is what we can say state vector, and what are the variables represented in the state vector. Now some of the definitions which we need to know or understand in this state space variable analysis. So what are those definitions, or what are the terms which are used in this state variable analysis? First one is state, then state variable, then state vector, fourth one is state space, fifth one is state trajectory. So these are the terms which we are going to use in this state variable analysis, and what are these definitions of different terms which you are using here. Okay, so in this we have First one is state. So what is the state which I have discussed? The state of any dynamic system is defined as it is minimal set of variables, such that the knowledge of these variable means at this particular variable, knowledge of these variables which I have given, that set of variables, okay, at t equal to t0, I mean t naught, together with knowledge of inputs, for t is greater than or equal to t naught, which completely defines or completely determines the behavior of the system. The behavior of the system. So what is the state is nothing but, this is nothing but minimal set of variables, which are those variables which such that the knowledge of these variables at time t is equal to 0, together with the knowledge of inputs for t is greater than or equal to t naught. Means whatever the knowledge of inputs which you have and the set of variables which is at time t is equal to 0. So together we can call it as the state, which determines the behavior of the system. It will behavior of the system. So here two things which we need to know. It consists of knowledge of the variables at t is equal to 0, okay, and it consists of knowledge of the inputs for t is greater than 0. So these two things together we can call it as a minimum set of variables which completely determines the behavior of the system. So it is a minimal set of variables such that the knowledge of these variables at time t is equal to 0 and as well as knowledge of the inputs for t is greater than or equal to the 0, together we are going to determine the behavior of the system. So now second one, state variable. Second one is state variable. In the state variable, the variables which are involved, the variables which are involved in determining the state of any dynamic system are called as state variables. So here it is very clear that the variables which are going to involved, which are the variables which are involved in determining the state of the dynamic system. The variables which are involved in determining the state of the dynamic system are called as state variables. Okay. So next definition is state vector. State vector. So when I say vector, it is if you have n state variables, which are necessary to describe any system. Say for example, I have n state variables to describe this to describe the complete behavior of the system. Say complete behavior of system. That is, we have x1, x2, x3, and so on, xn. So these state variables, which are used to describe the complete behavior of the system, can be considered as n components of vector x of t. So whatever the n state variables which we have used, that is x1, x2, x3, and so on, xn, to describe the behavior, that is dynamic system, complete behavior of the dynamic system, those are considered as n components of the vector xt. Means I'm going to represent the state vector x of t is the vector sum of all the state variables. You can say vector sum of all state variables. So the state vector x of t we can write as it is the sum of all vector variables. Okay, right. So now we can say state space. One more definition. State space okay. So state space is nothing but it is the space we have. Say for example, it is at x, y, and we have a point in three-dimensional. Say we can say three-dimensional. Then we can say it is the space. The space whose coordinate axes are nothing but the n state variables with time as the implicit variable is called as a state space. So state space is defined as it is the space whose coordinate axis nothing but n state variables. So if I have two variables, say for example x1 and x2, so this is called as state space. This is called as state space, which is found by these two variables x1 and x2. So the space whose coordinate axes are nothing but the n state variables with the time as the implicit variables, of course, x1 of t and x2 of t. Okay, and the state trajectory, the last definition, state so state trajectory is locus. It is trajectory means it is a path which is created. Okay. Similarly, it is called as locus, path or locus of the tips of state vectors. Okay, so at time t is equal to t1 and time t is equal to t2, say for example there are two variables x1 of t and say this is x1 of t and say this is x2 of t, and I have a variable x at t1 and this is the state vector at t2. So say this is the 2 points which is I have written as at this is the state followed by the variables x1 and x2 at time t is equal to t1. Then at time t is equal to t2, then this is the state is followed in this path. This is the locus which is plotted for the system of dynamic system at t is equal to t1 and t is equal to t2. So that is, we can say take it as x of t2. X of t2 is this one. This is x of t2. So the trajectory is means how from x of t1 to x of tt. So this we can say trajectory. So this one we can say trajectory, means from x of t1 to, I mean at time t, at t is equal to t1, at t is equal to t2, how the system is moving from this to here, it is moving in this path. So this one is called as trajectory. So it is a locus of the tips of the vectors, means see this is the tip of the vector x of t1. At time t is equal to t1, we have the state vector. At time t is equal to t2, we have the state vector at x of t of x of t2. So this is the tip of the, means I can say this one and this one are called as tip of vectors x of t1 and x of t2. So joining these two tips is called as locus of the tips of the state vectors, is nothing but trajectory, nothing but trajectory. So this is how we can define all this with the variable x1 and x2. So what is meant by state? What is meant by state variables? What is meant by state vector? What is meant by state space? What is meant by state trajectory? So these are the definitions which you have discussed now. So now we need to understand first state model, and then we can go for state model. Is consists of state equation as well as the output equation. So that we discuss in the next class.